Okay, so next problem we're going to take a look at. A mechanic pushes a car of mass 2,688 kilograms from rest to a speed v. Oh no, we don't know what the speed is. Doing 3,341 joules of work in the process. During this time, the car moves 51 meters. Neglecting friction, so we're going to ignore friction, between the car and the road, what is the final speed of the car? Okay, so I've got a car, and a mechanic is pushing the car, and is pushing it with a force. Let's see. Nope, they don't actually give us the force, do they? No! Okay, but the mechanic is pushing on the car, and pushes the car some distance, in my numbers, 51 meters. They tell us that the work that the mechanic did is equal to 3,341 joules. That's how much energy the mechanic has transferred into the car by pushing on it over some displacement. The mass of the car is 2,688 kilograms. All right, let's see. I believe that's all my information. Okay, neglecting friction between the car and the road. What is the final speed of the car? Okay, well, this is another application of work-energy theorem. They've given us the work, the amount of energy that the mechanic has put into the car. Since we are neglecting friction, there's no friction to steal any of that energy. It's not going to take any out. So all of that energy gets put into the car. Well, let's take a look at what type of energies we're going to have. Clearly, the car is going to start speeding up because we've been told that it's going to end at some speed v that they want us to find. So kinetic energy is definitely in play. They're on flat level ground, so they're not going up anywhere, so that probably rules out any potential energy due to gravity, at least any change in it, and that's what we're looking for. And I don't have any springs in this, so it turns out that when I say that work is going to be equal to my final energy minus my initial energy, delta E. In this case, the only energy that I need to take a look at is my kinetic energy. Okay, well, my work is going to be equal to my final kinetic energy, 1/2 mv final squared, minus my initial kinetic energy, 1/2 mv initial squared. Well, let me double check what it said, but I'm pretty certain. During this time, the car moves 51 meters. In this case, I can tell you this, we're going to assume that the mechanic has started pushing it from rest. I believe that should have been part of the question. It's kind of implied, but what that means is our initial velocity is actually going to be 0, which means our initial kinetic energy is 0, so our work is going to be whatever kinetic energy we have at the end, because that's where that energy is coming from. Well, now that we've got that, we know that the work is going to be equal to 1/2 mv final squared. And V final is what we're looking for. Well, we know that the work that we've done is 3,000, or that the mechanic has done. I shouldn't take credit for the mechanic's work. 3,341 joules equals 1/2 the mass of the car, because that's what's getting the energy, which is 2,688 kilograms, times V1 squared. I'm going to multiply both sides by 2 and divide both sides by 2,688 to try and get V final squared by itself. So 3,341 times 2 divided by 2,688. And I get the following, that 2.49 joules divided by kilogram is going to give me meters squared per second squared is equal to V1 squared. So I take a square root as my last step, and I get 1.576, so we're going to call that 1.58 meters per second equals V final. We got 1.58, survey says 1.576, actually they got the exact value that I have in my calculator here, so it should accept it just fine. All right, now that's not the end of that question. Now that we know how fast the mechanic has got this going, they ask another question. I think, yes, what is the horizontal force exerted on the car? Basically, they're asking what I mentioned offhand before, how hard is the mechanic pushing? That's the force in the horizontal direction that's acting on the car. It's the mechanic pushing on it. We're ignoring friction, So there's nothing else in the x direction. All right. Here's where we use the other side of work. We can use the work equation. So we're going to say that the work is equal to the force times the displacement times cosine of the angle between them. Okay, well, we want the force. We know the work done. We saw that just a moment ago. That was 3,341, I believe. 3,341 joules. That's the work done by the mechanic. We want the force. That's the thing we're looking for. And the displacement, well, they told us that the mechanic applied the force doing the work over a displacement of 51 meters. Cosine of the angle between them, let's look at our picture. Our force is to the right, and the car, our displacement, is also to the right. Both vectors point the same way, so when they both point the same way, the angle between them is actually going to be 0. So cosine of 0 degrees. Well, cosine of 0 degrees, plug it into your calculator to double check, but it's actually 1. Sine of 0 is the one that goes to 0. So that's just 1. So I'll take 3,341, divide it by 1, and divide it by 51 meters. Then I'll have a joule per meter, which is actually a newton. So I'm going to end up with the following: 65.5 newtons equals the force applied by the mechanic, assuming it's a constant force, which is fine. The mechanic's probably pushing with a constant force. And so we end up with, let's see, correct answer, 65.5 newtons. This is how you would go about and solve.